Welcome viewers to the NPTEL lecture series on the calculus of variations. This is the sixth lecture of the series. Now, we will start the discussion on the main topics. We will start with the fundamental concepts of the calculus of variations. Here as we had mentioned in the first lecture that certain problems initiated the study of the calculus of variations. I would mention three main problems here. The first one was already mentioned, that was the Brachistochrone problem introduced by or proposed by John Bernoulli in 1696, and then subsequently there were many problems added to the discussion of the calculus of variations, like geodesic, finding of geodesics, and then isoparametric problems and certain problems of mechanics and physics. They were formulated as optimization problems, that means finding minimal or maximal values of certain functionals. So, here I would mention here three main problems which initiated the study of the calculus of variations. The first one is here finding the length of a function, like you have in the x y plane, and there are 2 points A and B, and a curve joining, a smooth curve joining this. We know that the length of this curve is the functional, that is square root of integral over, let us say this is the point x 1 and y 1 here, x 1 x 2, and this is the point x 1 y 1 and x 2 y 2, and so we need to find this integral x 1 to x 2 integral x 1 to x 2 of this d s, where s is the arc length and it is given by x 1 to x 2 square root d x square plus dy square. This is a plane curve. So, we have x and y variables only. In general, if we have 3 dimensional curve, then d s would be square root of d x square plus dy square plus d z square. So, here there are only 2 variables. So, we have this. Now, if we treat x as parameter and take y as a function of x, then if we take y as a function of x like this. So, this is y x, for each x here the value this is x y comma y x point on the curve, that is the graph of the curve. Then this L y is given by x 1 to x 2 square root. So, this becomes 1 here. So, x is a function of x itself, that is the identity function, and so dx by dx gives you 1 plus dy by dx square, and this dx comes out here. Now, x as a function of t, y as a function of t, and t has range t 1 less than t less than equal to t 2, then L y can be given as t 1 to t 2 square root. Then we take dx by dt square plus dy by dt square, and then this dt comes. So, we can use any of these as functional defining the length of the curve y. So, here we need to find a curve such that the length is minimized, and we know the answer is the straight line joining these 2 points A and B. So, this is the first elementary problem of the calculus of variations. The next one is, we have seen that the surface area A s is given by, we know that this is double integral over the surface S of the element surface area d s. here you have 3-dimensional figure x, y, z, and this is the surface bounded by the curve, let us say C here, and this is surface S. So, here element area is d s, and we have seen that this the outward normal becomes actually we need to fix which one to define as outward normal, because there are two directions, one is the upper one and then the other one is in the down side, that is also the normal to this surface. So, which one to call outward? Here we take the convention that we take this curve C as positively oriented when we take this as anti-clockwise, and if we consider this situation, the same surface is here and we take the positive direction of C like this, then and the element d s is here, then the normal will be downward like this. So, we have to see that here the positive direction of C, that means this is an oriented surface. The upper side here is taken like this when the direction of this curve bounding this surface, actually we are considering the downside of the surface, and then the positive direction is the reverse direction of the earlier one, and so and outward normal in then will be the downside downward normal to the this one which we had considered, just minus of this n cap here will be the n cap in this situation. So, we need to fix the orientation of the surface at the beginning, and then see which side we are considering as the positive side of the surface. So, here this we had seen that d s is actually, now here if we parameterize S as like position vector of this point P here like this. So, this is position vector, that is R here, and it will be a function of two parameters u v. So, we take x u comma v I plus y u comma v j plus z u v k, that we had already explained, and then we know that this element area d s is nothing but R u cross R v, absolute value of that d u d v. And so, here now actually we know that this one can take as, so it n cap. So, this will be nothing but A s will be over this S, and absolute value of this n cap d s. So, this is what we have as d s. Now, this n cap d s will then be, now if you define this capital N as R u cross R v, then we know that this is normal to the surface, because this R u and R v constitute the tangent plane, and so R u cross R v gives you normal to the plane described by R u and R v vectors, and so this n cap is the unit normal, which will be nothing but n cap, this capital N cap and arrow over this absolute value of this vector n. So, that is what will be the unit vector in the direction of the outward normal, and so we can see that then this capital N will be given by n cap absolute value of capital N, and so therefore, this A s can be seen that the surface area will be here will be given in the projected one. Let us say this R is the projection of this on the u v plane, rather here we are taking x y. So, we will take that a particular case here this is d, this is a projection of the surface on x y plane, and if we take projection on u v plane, that we will denote by r. So, r, and so this will be nothing but absolute value of capital N du dv, because absolute value of n cap is 1. So, that is what we will have, where r is the projection of S on u v plane. So, that is what will be the formula for finding the surface area. In particular, if we take this case where surface is projected onto x y plane. So, this is the surface and it is projected on this x y plane like this D, this is the surface S, and so in this case, in this special case, our position vector r is given as x I plus y j, and plus let us say this surface is given by z as function of x y. For each x y here, this gives you the point this p here, which is x y and z x y like this, which we have already described earlier. So, this will be the position vector in this special case. Usually, if we take u v as parameters, then this x y will be functions of u and v, but now we are taking x and y as itself as parameters, and then z is a function of x and y. And then in this case, you can see that n, which is nothing but r x, now u is x. So, r x cross r y and v is y here. So, this is nothing but I plus z x k cross product j plus z y k. So, this is the nothing but I j k and 1 0 z x here and 0 1 z y. So, that is I times this 0 minus. So, minus z x I, similarly j will give you minus z y k j and plus, and then k component is 1 here k. So, this is what is actually capital N here in this situation, and if we take the downside, then we will have to take r y cross r x, which will be minus of n and will be pointed downwards in the case when we take the other as the reverse direction of this as positive orientation, positive direction of C. So, then that will be the orientation of the surface will be just reverse, that will be from the downside of this surface S with here. So, here in this case, so we substitute in this formula that A S is equal to absolute value of this cap du dv over this projection is now on r is now d, this one over d, and this is actually dx dy, u and v are x and y respectively. So, this is nothing but, and so absolute value of this gives you square root 1 plus z x square plus z y square and dx dy. This is what we had already seen this formula. So, this is the proof of that result given here. So, here in this case this surface area where it is taken x y taken as parameter, the surface area is given by this formula, and so this is a function of, so this here L of z, you can take like this, square root 1 plus z x square plus z y square dx dy. So, this is another more general functional here. So, if we change z, then this number L is going to change, L z is going to change. So, this is a functional defined like this on higher dimensional spaces. So, I would mention now these other problems, main problems. That first one was mentioned, that which was Brachistochrone problem. Which was described earlier. It is in the vertical plane, you have to take. So, we take this one point A as the origin itself and the other point B like this, and here we join this by a smooth curve, this y. So, this is x axis, this is y axis, and we take this point as the shifted to the origin itself, and so this is the curve y x, and the point is sliding under gravity. So, we need to find the time, which we have already seen that this time t will be given by, which will be a function of y, and it is integral x 1 to x 2. So, here anyway x 1 is 0. So, 0 to let us say 0 to some x 1 here, and this will be d s over v, and so we will have this 0 to x 1 d s. We know that it is square root 1 plus y prime square d x, and v here. Now, this v is, we know that v square equal to u square plus twice g h. So, u is 0 because it is dropped from here, there is no force applied here, initially it is just at rest. So, u can be, u will be 0, and so that we can see that using this formula we see that v, this v is actually root 2 g y, h height is actually taken now as y. So, substituting it here, we see that t y comes out to be 0 to x 1 square root 1 plus y prime square d x over root 1, we can take this constant out, root 2 z, and whole like this y. So, this is the functional which for the Brachistochrone problem, and we once we develop sufficient machinery to see that what are those functions which optimize this, which give the least value, we will see that the solution of this problem is actually cycloid. So, the y turns out to be cycloid, y is actually cycloid. This is what will be answered once we have sufficient tools developed for solving these problems. The other one is the problem of geodesic. This is the generalization of this problem. Here in this we have plane surface here, the plane x y, and there are 2 points, and we want to find the minimal length joining these 2 points, and we see that in this case answer will be straight line, but in the more general problem like this, we have, for example, here the surface S is like this, its projection is D here in this case, and this Z is given as function of x y. Now, here we take 2 points on this surface A B, and then the curves joining this on this surface. So, there is a point A here, this point B, and this is the curve join these 2 points. We want to find the minimal the curve which has minimal length, and this curve has to be on the surface, and this should have minimal length. That means, you take any neighboring curve, its length will be more than this one. Such curves are called geodesics. So, in the plane thing, geodesics are straight lines. Here like on spheres, these are great circles and so on. We can have various other like cones. On that also there are nice geodesics, which we will be discussing in subsequent lectures. So, here how do we formulate this as a problem of the calculus of variations? So, here we know that again this length formula will be given by so length of the curve. So, here on this we can parameterize this curve like x of t, y of t, and z of t like this. So, let us say and z as, and t has the range between t 1 to t 2. So, that is what will be parametrically this curve will be described by these 3 equations, and so then L will be given by t 1 to t 2 here d s, and that is t 1 to t 2 square root d x square plus d y square plus d z square, and so in terms of parameters t 1 to t 2. So, d x by d t square plus d y by d t square plus d z by d t square d t, and then these x y z must satisfy this. Z t must be z of x t y t like this, and so from this d z by d t must be z x partial derivative with respect to x, and then d x by d t z y d y by d t. So, like this. So, here there is a restriction that these points x y z must lie on the surface, and that will be described by this equation, and so we can substitute it here, and so this L can be given as, so this will be a function of z anyway, and so t 1 to t 2. Here we will write short notations like x dot, dot means d x by d t, x dot square plus y dot square plus z dot square is this z x x dot plus z y y dot square root d t, and these z is again. So, z x, since z is a function of x y. So, z x and z y are also functions of x y. So, this is like t 1 to t 2 and square root of, so some functional like this of you have x y x dot y dot d t. Here t is not appearing explicitly, but in certain t may appear explicitly. So, this is more general case which we had considered. We had considered only like this x 1 to x 2 f x y y dash d x. Here there are more dependent variables y, t is independent here. So, we can put t also here, although this is not explicitly function of t. So, there are t is independent variable, x is a function of t, y is a function of t, and x dot y dot. So, there are more dependent variables here, there is only one independent variable, more dependent variables x and y. So, this is a situation which we will be dealing with later. So, this is the problem of finding geodesics on surfaces, and then the third one is isoparametric problem, which was mentioned earlier. So, this was considered in ancient time by Greeks, where areas of certain surfaces were to be found such that their boundaries are of fixed length. So, that is what is known as isoparametric problem. Iso means same, parameter, their parameters should be same. So, here you have situation like this, certain curve is given of fixed length and this is the area here. So, this is the domain D, let us say in x y plane, and this C is having fixed length. So, we need to optimize this area of D such that the length of C does not change. So, that is what is isoparametric problem. We know the answer is disk here, D has to be. So, this C has to be a circle and D has to be the inside area of that, that means it is a disk, and so that is the answer which we will be getting when we have sufficient tools to study these problems. So, here how would you pose this? We have seen that this area can be given, area of D, by using that Green's theorem result. We can see that it is given by half of integral over C y dx minus x dy like this. So, here and this length is fixed here C. So, what we again take this as a C as a parametric thing. So, with this we will, if we take x as function of t, y as function of t, then this area of D is given by 1 by 2 T 1 to T 2. Here this range is y t dx by dt minus x t dy by dt is x dy by. So, this is x dy or minus of this we can put here. So, minus of this. So, this is actually x dy minus y dx. So, we can put minus sign here like this. So, here we will have this one, and then the length of this C curve is given, that is T 1 to T 2 and square root dx by dt whole square plus dy by dt whole square. So, this is what is to be done here, and so we use here Lagrange's method of multipliers, and so we can take the functional like this T 1 to T 2 here y x dot minus x y dot minus of this. So, let us put that minus sign inside. So, x y dot minus y x dot plus lambda square root x dot square plus y dot square and dt. So, this will be the functional which we will consider here. Lambda will be Lagrange's multiplier, which it is undetermined, it will have to be determined. We need to find this x and y as well as lambda here. So, this can be taken as a functional f here, and again you have only t is not appearing explicitly, f as a function of lambda also is there, x y x dot y dot dt. So, this kind of function optimizing. So, these are three main problems actually created lot of interest in the theory of the calculus of variations. And so, here now what are the tools which we use in order to see that to answer these questions, what are those curves we optimize, which optimize these functionals. So, here we need to find certain conditions which are known as necessary conditions. It is an Euler equation actually known as Euler's condition, which is to be satisfied by that. So, that is what we will be deriving in these lectures. And so, let us first understand how we are going to consider the variations of these functions here. Now, first let us see that how we do it in case of functions. So, here we have a function f on that interval, let us say a b to r, and so this is the case here a b and function is like this, and around x we can see that such that x plus delta x is also in that interval. So, x and x plus delta x being in this a plus a comma b in this interval. So, then f of x plus delta x minus f of x should be, if this function is differentiable, then we say that this has to be like this a delta x plus some beta, which is a function of x delta x times delta x. So, here so we consider here a function f from a comma b to r, and this is the situation here, this is a b and x is any interior point here, and x plus delta x is also in that interval. So, delta x is the increment in x. So, if f is differentiable, then we in fact f is differentiable if and only if the following holds, that f of x plus delta x minus f of x is a times delta x. A is a constant here, not a function of x or delta x, and plus this term beta x comma delta x delta x. Here this beta x delta x, this tends to 0 as delta x tends to 0. So, we can see that if we divide by delta x, so we know that f of x plus delta x minus f of x divided by delta x, it gives you a plus beta x delta x, and this goes to a as delta x tends to 0. So, clearly then a has to be f prime x. So, this is the linear part in the increment here. See, f x is this delta x is the increment in x, and this is delta f given by f of x plus delta x minus f x. So, this increment in f is actually a times delta x plus beta x comma delta x delta x. This function beta is assumed to satisfy this condition. So, f is differentiable if and only if this holds. This is let us say 6.1. So, 6.1 holds if and only if f is differentiable, and we can see that we divide by this delta x here. So, this delta f by delta x is equal to this, and this tends to a as delta x tends to 0. Therefore, we know that this is used for derivative f prime. So, follows that A has f prime x. And so, here this part is called linear part in the increment, because it is linear in delta x. So, and that, so this A, or rather, so therefore, this delta f is actually f prime x delta x plus beta x comma delta x delta x. Here this is the linear part in the increment, of f, and so this is what is called differential, and so this is called differential and denoted by df. So, df is actually f prime x delta x. So, this is the differential of f, and this clearly prime x is the differential coefficient, because the coefficient of the differential delta x here, because now if you take f x equal to x, we know that dx equal to delta x, and so we can replace this. If we take this, then dx is equal to delta x. For this independent variable, this increment is same thing as differential, and so df equal to f prime x dx. So, that is what we frequently use, that we just say that dividing by dx we get actually, which is a layman's language of saying that you divide by dx and you get f prime x. So, but in the case of two variables, what happens that if you have f as a function of R 2, or rather a domain in R 2 to R, and then you take any point x y in x y and x plus delta x, y plus delta y, these points in D, then f of x plus delta x. So, delta f here again comma y plus delta y minus f of x y is given by, in the same manner it will be a delta x plus b delta y plus some beta x y delta x, square root of delta x square plus delta y square times square root of delta x square plus delta y square, such that this beta x y square root delta x square plus delta y square goes to 0, as square root this delta x square plus delta y square goes to 0. So, we say that f is differentiable if the following happens, that this is, let us say this is 6.2. So, 6.2 holds if and only if f is differentiable, and we can again see that if we divide by delta x and fix delta y, we do not change delta y, only delta x is changing and delta x tends to 0, then if you consider this like this delta x, then we have a plus b delta y delta x plus beta x y square root delta x square plus delta y square, and here times square root delta x square plus delta y square delta x. So, this goes to a see, we take, let us say we take delta y to be 0. So, take delta y to be 0, then we see that delta f over delta x is a plus beta x y delta x, and then like this, and you have, so this goes to 0, this goes to a as delta x tends to 0, which is the particular case because delta y we have taken 0 here. So, this condition will be satisfied and so this is what is actually. So, a now this is nothing but del f by del x, the partial del. So, a has to be then this goes to in the limit of delta x tending to 0. Okay. So, let me put it here. Limit delta x tending to 0 of this. So, this is actually equal to a. Similarly, we have delta f or delta y will turn out to be b. So, we can see that here this delta f is actually f x partial derivative delta x plus f y delta y plus beta x y square root x square plus delta y square root delta x square plus delta y square. And we have this as delta x is same thing as dx plus f y dy plus beta x y square root delta x square plus delta y square root delta x square plus delta y square. And so, this is the linear part in the increment, linear part in the increment. Because this is linear in this delta x, which is nothing but dx, delta y, these are independent variables and therefore, delta x will be same thing as dx, which we have seen, and delta y will be dy here, and so this df will be given. So, that linear part is called the differential, and so df is given by f x dx plus f y dy. So, that is the situation for functions. Now, let us see in the case of functionals. So, we have I y here. Now, we give increment to, like we gave increment to x, we give increment to y, and what happens to the increment to I. So, this is the functional I here. So, if we consider this y plus delta y. So, what is that delta y we mean, and what is the functional this, and then delta I will be given by I y plus delta y like this minus I y. So, how do we define this? That is what is to be seen. What is this delta y here? So, what we do here, let us say we have, and there are these 2 points A and B, and this is the curve y x, and this is the neighboring curve y 1 x. So, these y 1 y x and y 1 x, these are joining these 2 points A and B. So, this is the point x 0 y 0 or x 1 y 1, and this is point x 2 y 2, and these are two functions y x, and let us say let us not use y 1 here, let us say this is y tilde, the neighboring curve here. So, this delta y as a function of x, this is the difference, this y tilde x minus y x. So, at each point here, this is x 1, this is x 2 here, and so at this point x, difference here y x is here, y tilde x is here, and y x is here. So, this is this difference of these ordinates is what is delta y x.
So, as x moves from here to here, we get this various values of delta y. So, this is the increment in y, and now what happens, this I, which will be a function of y plus delta y. Now, here I of y plus delta y and minus I y. So, that is what will be denoted as the increment in the functional or variation in the functional. In the same manner, the situation here. So, how do we define the here the actually things here, like we had x going to x plus delta x, the difference is delta x. Now, here we have seen that this delta y is there, we are saying that this y tilde x is near to this, in what sense, that is what is to be made precise here, because this functional x 1 to x 2, here you have f x y x and y prime x. So, it involves y prime x also, y x as well as y prime x. So, what is the variation in y prime x, that is to be seen. For example, if you take this situation, that this is point A and B. Now, these two curves like this, if you consider, or this the other one, one curve is like this and the other curve is going like this. So, although this is also close to the, let us say this is the original curve, y x is this and this is y tilde x. So, y x is the straight one, this one is y x and the curved one is y tilde x. So, we see that though this delta y x is y tilde x minus y x here, and in this case also we will have delta y x will be the same thing here, and so we see that here the variation will be too much in the derivative. So, here although this, if we define this delta y prime x will be y prime x minus y tilde prime x minus y prime x. So, here in this case both these will be close enough. So, if this is less than epsilon, let us say, then this will also be similar to the epsilon distance, but here this thing will be difference will be too much in the case when we take derivatives here. So, we need to define the closeness in the sense of order of proximity. So, that is what we will be considering now. So, we define here the concept of proximity of order k. We say that y tilde x close to each other in the 0 order proximity if for every epsilon greater than 0 there exists delta greater than 0, such that if x minus x dash. So, here this, or let me write, okay. So, this y x, absolute value of this y tilde x minus y x then epsilon provided here. Okay. So, this is called epsilon order of proximity. If for every epsilon there we say that y x and are close to epsilon to epsilon close rather close to each other in 0 order of if we have the following thing for all x here. So, this rather we can say maximum over x less than x 1 less than x 2, this is less than epsilon. Now, we generalize this, we say that y tilde x and y x are epsilon close to each other in first one order proximity, or rather first order proximity if maximum of x 1 less than x 2, this y tilde x minus y x is less than epsilon also, and maximum x 1 less than x 2 y tilde prime x y prime x is also less than epsilon. So, this can be generalized, and so k order proximity similarly y tilde and y are epsilon close in kth order proximity if this y tilde jth derivative x minus y jth derivative x is less than epsilon for j equal to 0, 1, 2 up to k. 0th order 0 means then the function itself. So, that is what. So, they are not only closed like this, see these are only 0 order close, not the first order, whereas this is for first order close, first order proximity of these curves y and y tilde. So, like this we will be considering the various concepts continuity and differentiability as we consider the for functions. We will be defining the variations of functionals in the next lecture. Thank you very much for viewing this.